Hello everyone. So this is the 35th International Mathematical Olympiad or IMO 1994 problem number 1. Let m and n be positive integers and let a1 to am be distinct elements of 1 to n such that whenever ai plus aj is lesser than or equal to n for some I and j between 1 and m, there exists k between 1 and m with ai plus aj equals to ak. Then prove that the average of a1 to am is lesser than or equal to n plus 1 over 2. You may pause this video and give it a try on this problem before you watch the solution. Now let's begin. So first, since we have a1 to am are distinct elements of 1 to n, we can, without loss of generality, assume that a1 is lesser than a2, lesser than a3, and so on until am. Alright? Now, maybe we can do some observation. Maybe we can take a look. What if I have a1 plus am is lesser than or equal to n? Therefore, I have k such that ak is equals to a1 plus am, which is larger, strictly larger than am, which is impossible because this would make us have k larger than m, which is impossible or contradicts with the fact that k is between 1 and m. Therefore, we must have a1 plus am is greater than n. Now let us observe the next case, where we take the next element, which is a2, and the second largest element, which is am minus 1. What if this is also greater than or equals to m? Okay, so we have k, let's say ak equals to a2 plus am, which is greater than am. But in this case, we also have a1 plus am minus 1 is lesser than n. Therefore, we have another k, or let's say l, such that al is equals to a1 plus am greater than, this must be am minus 1. Alright, so we have two distinct elements, ak and al, which are larger than am minus 1, which contradicts the fact that the element that is larger than am minus 1 is only am. Alright, so let us say, for the sake of better writing, we let the big A is the set of ai, where I runs from 1 to m. Okay? Alright, by the way, from this observation, maybe we can see that, or guess, for every I, we have ai plus am minus I plus 1 is greater than n. And how we prove it? We just assume that this is lesser than or equal to n and use the same or similar argument. So let us try. All right, now let us say for or I with 1 lesser than or equal to I lesser than or equal to M, we assume that AI plus AM minus I plus 1 is lesser than or equal to N. And let AJ equals to the set of let's say this is the set of let's say this is the set of the set AI, which is the set of AJ, where we have J is greater than M minus I plus 1. Okay, so you'll get to see it why I choose this construction of AI. So now observe that all elements of the set B, let's call this BI, where BI is equals to AJ plus AM minus I plus 1, where J is less than I, less than or equal to I. So now observe that all elements of the set BI, where BI is equals to the set of AJ plus AM minus I plus 1, where J is less than or equal to I, this less than or equal to 1. So this means that BI contains of A1 plus AM minus I plus 1, then A2 plus AM minus I plus 1, up until AI plus AM minus I plus 1. Alright? Okay, so observe that all elements of set BI, let's say this all element X of this set BI, where BI is this function defined here, we have X is lesser than or equal to N. Okay? Therefore, there exists, let's say this is KJ, where 1 lesser than or equal to J lesser than or equal to I, such that AKJ will be equal to AJ plus AM minus I plus 1, which is greater than AM minus I plus 1 for all I from 1, 2 until M. Which means that BI is a subset of AI. Why is it true? Oh, so because in order for AKJ to be larger than am minus I plus 1, we must have kj is greater than am minus I plus 1. Alright? So now, what's happening here is that since A1, A2, up until AI are all distinct, we have the cardinality of BI is equals to exactly I. But the cardinality of AI is equals to M minus I plus 1, which is equals to I minus 1. So this is impossible for BI to be the subset of AI. Contradiction. And hence we must have that AI plus AM minus I plus 1 is greater, strictly greater than N. Therefore, A1 plus A2 and so on plus AM over M will be equal to A1 plus AM plus A2 plus AM minus 1 up until the middle one, which is let's just like call it some AK plus AM minus I plus K plus 1. Oops. Okay, it seems like we need to divide it by I don't think we need to divide it by 2 cases. Sorry about that. Therefore, all right. So let's say we have 2 AI. Let's say we have A1 plus A2 plus A3 AM plus this is AM minus 1 up until A1 over M. Okay, this is equals to A1 plus AM, A2 plus AM minus 1 until AM plus A1 divided by M. This is greater than N times M over M. Alright, so why is the left hand side here? The left hand side here should be 2 times AM. Sorry, let's start with A1. A1 plus A2 till AM divided by M. So this is equals to N. Therefore, we have A1 plus A2 plus so on until AM divided by M is greater than N over 2. Okay, it seems that we are close to the conclusion of what the problem asks us to prove. So we will put some trick here where we know that all A or AI are positive integers. So if I have AI plus AM minus I plus 1 is greater than n, it also means that AI plus AM minus I plus 1 is greater than or equal to n plus 1. So we can write something over here, or AI plus AM minus I plus 1 is greater than or equal to n plus 1. And therefore, we have the following. So this n over here will be n plus 1 here, and this must be greater than or equal to. And the final one here will be n plus 1 over 2. And we had proven the problem as desired. So thanks for watching. I hope you like this video, and please don't forget to like and subscribe this video and share it with your friend, with a fellow Olympian, so that you will learn together. Good luck and see you on the next video.